One thing we always try to do in The Sky at Night is to take complicated subjects and explain them in terms anyone can understand. Quasars, pulsars and so on. I hope we succeeded.
Well, the tides, as you know, due to the influence of the sun and the moon. And when they pull together, as they're doing at the present moment, the pull is added, you see, and we get high tides.
Granted that the forces are enormous, just how big are they?
It's absolutely tremendous. There's no doubt at all of it. Also, the tides is the biggest natural force in the entire world.
Until you know the size of an object, you can't tell how far away it is. And the same applies to two lights. Look at these. They appear very much the same, but in fact one is much brighter than the other, and I'll show you what I mean. This is a powerful light. And this one is simply a small pocket torch. But until you knew that one was further away than the other, there was no way in which you could tell.
Will you please close one eye, doesn't matter which one, and then hold up your finger and line your finger up with my nose as you see it in the television screen. Got that all right? Now, without moving anything, use the other eye, and you will see that your finger is no longer lined up with my nose. And if you keep everything quite still and flick your eyes around like that, you will see your finger apparently flashing to and fro. Paul, representing 61 Cygni, the nearby star, is moving very obviously compared with the background stars. Not because he's really moving, but because the camera is. You can see there's a very obvious shift. Of course, in this, it must be exaggerated, but the principle is absolutely valid, and it does apply to the stars.
In One Sky at Night, I tried to show the principle of radar by throwing up a tennis ball and then catching it on the rebound.
If I throw a tennis ball against this groin and then catch it, well, if I know how fast the tennis ball is going, and I know how long it takes between my throwing the ball and my catching it, well, I can tell how far away the groin is.
I caught it on the 8th attempt. In 1968, we did a very interesting program about mysterious objects, pulsars. We now know what they are. They're rotating neutron stars. We didn't know then.
We were completely mystified. We thought the signals might be signals from intelligence, and it was only after several weeks that we had a closer insight into what these fantastic signals were really about.
Well, the first person to identify these strange things, we now call pulsars, was Jocelyn Bell, and she joined us on a program sometime later.
So we appeared to have a radio source that was sending out flashes of radio waves every 1 1/3 seconds. Suspiciously man-made, actually.
When did you decide that they weren't man-made?
Very quickly, because they went round the sky with the stars. They kept sidereal time, which means that it had to be something going round literally with the stars. I suppose it might have been a satellite in a funny orbit, but we eliminated that. And it couldn't have been anything earthbound, except possibly other astronomers, because they're the only people who keep time with the stars.
What then about the life story of a star? We decided to try and illustrate this, and I took part myself. I can picture myself as a red giant, but not have fancy as a white dwarf.
So what I propose to do now is to join the HR diagram. And I'd like you, if you will, to stretch your imaginations very considerably and imagine that I represent an evolving star. And at first, the light is unsteady. It's what we call a T-Tauri variable, and it joins the main sequence. And this is where it spends the major part of its active career. Then, after a very long period indeed, the supply of hydrogen starts to run low, and your star leaves the main sequence. And the outside swells out and cools down, the inside shrinks, and the star enters the giant branch. And of course, when that happens to the sun, it's going to be the end of the Earth.
What then about black holes? Probably the most bizarre things in the entire universe, so far as we know.
I've got here a pair of objects, a dustbin and a bag of rubbish.
Yes.
If I were to shoot this towards a black hole, a rotating black hole, and allow the rubbish to fall into the black hole, this will come whizzing out.
Yes.
With lots of extra energy.
Yes. Could we tackle something so abstruse as relativity? Well, we tried.
Suppose we imagine two-dimensional people like this little circle. The people have no idea of what 3 dimensions are. They are flatlanders. And let's imagine this as the world on which the flatlanders can move. this is spherical, but they don't understand the meaning of 3 dimensions. It's a flatland as far as they're concerned. Now, suppose we introduce a dimple into this. When this little person's moving across there, when he comes to the dimple, he suddenly drops in and whips out. And he says, hello, I've experienced a force. I've dropped in and I've come out. I've experienced a force. But I say in my wisdom, oh no, you haven't experienced a force at all. You have come across a distortion in geometry. You think it's a force. I, in my wisdom, know that you've merely had a change in geometry and you interpret that as a force.
But if space is curved and finite, then what's outside it?
Oh, that's not a fair question. You see, you're asking me a 4-dimensional question, and I'm not a 4-dimensional person. I can't think 4-dimensionally.
Here I am, in a lift, going 3/4 of a mile underground in Boulby Mine toward this strange observatory. Why are we going so deep?
Well, we are going to look for dark matter at the bottom of the mine, and the reason why we need to go underground to look for it is to shield this very sensitive experiment from the deluge of electrically charged particles that are always raining onto the Earth, the so-called cosmic rays, which would interfere with this very sensitive equipment.